Hello everyone, welcome back to my channel Deep Understanding of Research Papers. Today in this tutorial I will explain the paper End-to-End Deep Neural Network Age Estimation. This paper was published in Interspeech 2018. This paper is from JHU CSLP lab. So the tutorial is going to cover the overview of the paper. Then we will see what is age estimation using speech or from speech. Then we will see X vector based age estimation method which is proposed in this paper. Then we will see the data sets used and the experiments, and finally we'll see some results. So basically this paper talks about estimating age of a person from his audio, from his voice. So they use this X vector approach for this age classification, and this X vector is becoming is a very well known approach in speech. They have people have used it for speaker identification, language identification, and many more problems, and it consistently showed that this can beat the state of the art any speaker recognition or even language identification tasks. And this age estimation using speech is also inspired by this X vector method, where they take this approach which is similar to speaker classification, and they try to use the same kind of approach here to show that this works better than I vector, which is one of the very well known methods in speech for any speaker identification or even language identification problems. And many importantly, they show how to combine this regression and classification objectives together to optimize this X vector network to get a better performance. Then they show that this can beat the state of the art results on SRE dataset, which is speaker recognition challenge dataset, which has this age category, age classes also for every audio. And this actually beats the I vector system with a margin of 12% absolute error improvement. So that's a very good point where they have 12% improvement over I vector system. So what is age estimation? So age estimation from audio is basically estimating the age of a person by his recording. This age estimation is also there in image or computer vision, where they estimate the age of a person using his face. Same thing can be done with audio also. We can estimate the age of the person just by listening to his audio. And as you can see here, we want to know somebody is speaking here, we get this audio data, and we have some age estimation model here, which can be any model which you have, like X vector, I vector, or whatever GMM, HMM kind of model. And the system should output, or system should understand the audio and estimate or predict what is the age of this person. And you can think of this prediction in two ways. One is you can think of this as a regression task, where you want to generate some value in the linear scale which tells you what is the age of a person. Or you can classify this audio into one of the, let's say, 10 classes. So each class can be a bin. So bin in the sense, you can say the first class is any age between 5 to 10 years, or second class is 5 to 15, 10 to 15 years, or 15 to 20 years. So those are the bins. Those are discrete value. You can classify them, or you can do a classification. You can think of this problem as a classification problem, or you can think of this as a regression problem, where you predict the age of a person in the linear scale. You may get values, or you may get data for like 1 year, 2-year-old, 3-year-old, 4-year-old, 10-year-old, 12-year-old kind of data, and you just regress over those numbers and finally generate a number in the linear scale to get the age of the person. So in this paper, they showed how to combine this regression task or regression objective and the classification objective together to get a better performance. We'll see that in the coming slides. So now, what is X vector based age estimation? First of all, let's understand what is X vector. We know what is age estimation. We just want to predict age for a given audio data. Uh, and as we said, we have been telling about this X vector. So we'll see what is X vector. So X vector is basically a deep neural network. It's a system, just like I vector. I vector is mostly GMM kind of model. You can do DNN based I vector also, but think of this X vector as some sort of neural network architecture, which uses some components like time delay neural network and max pooling, sorry, statistic pooling, and classification layers, and estimates, or it gives takes the which takes the input as audio variable length audio data or a variable length audio recording, and predicts or generates an output. So basically, what we are showing here is this is the main full architecture of the X vector. We have there is something called time delay neural network. So the time delay neural network is some sort of 1D convolution kind of architecture where you have some data, and you consider fixed length filters, and you move those filters over time, and you generate the responses, and the higher level will again look at some window and generate responses from that layer. Finally it goes to the final layer. So these layers here, what we are seeing here, these are time delay neural networks. And as we know, the audio can be variable length. It's not like fixed 5-second audio we can feed it to a convolutional neural network. Here we can have a variable length audio. What we are going to do is, for each segment could be like a 10 frames window or 20 frames window or 3 frames window. So we can take that segment and feed it to a convolution time delay neural network, which is this blue part here. This blue part will generate one vector, which looks like this. Then we move the window and we feed it to the same time delay neural network and generate another vector. So if we cover this entire time capital T, let's say we had T capital T frames, T could be 100, 1000, anything. We get if T is 100, we get 100 different vectors here. So those vectors so can vary if the T varies. So if this 100 will become 200 if capital T is 200. So if we have 5-second audio, let's say we get 100 frames. If we have 10-second audio, we get 200 frames. But what we want is, we want one vector which will characterize, or which will tell us the entire which will give us some sort of high level representation for this entire audio. So what we are going to do is, we are going to take all these vectors and compute the mean and standard deviation vector out of these 100 vector, for example. So this mean vector and standard deviation vector, we will concatenate together and make it as a single vector. This mean and standard deviation vector, this mean and standard deviation block will give us one vector, which we are going to feed it to a deep neural network or feed forward neural network. Let's say there are two deep feed forward neural network, and the final one, it goes to softmax, and from the softmax we can predict what is the age of the person given this xi, which is this input audio. So that is X vector system. Basically, X vector system has the statistics pooling layer, which will pool all the frames, or which will pool the high level representation for every frame, and create one vector which will give us the full representation or full high level representation of the entire audio content. And that we are going to use it for classifying the audio into one of the age, or regress over this linear scale. And these vectors, whatever we learn, those are like discriminative vectors, highly discriminative vectors. So if you use the same concept in speaker recognition, these vectors, whatever we get here, those vectors will be after this pooling, whatever vector we generate here after feed forward, those vectors will be highly discriminative vector, and we can use them for transfer learning. Like if you want to, let's say, do let's say you want to create a speaker recognition engine for your own content, you can take some pre-trained model which was trained on thousands of speakers. Then you can do transfer learning using these sort of high level vectors. And these kind of things are also done in image, where you have some pre-trained model like VGG or Inception, and you can extract high level features from them and use them for classifying your own data, right? So the same thing can be done here. So this is X vector. And most importantly, what we should observe here is they have combined regression loss and classification loss together here for the final loss. So usually, as I said, you can pose this problem of age classification as classification problem, where you classify every audio into one of the bins which are discrete. But or also you can do one thing, like you can do regression, like you can regress over the linear scale, let's say from a 5-year-old to 30-year-old or even 100-year-old person. So you can generate like numbers, like integers or real value numbers using this same network. But there are advantages for both of them. So what we are going to do is, if you use bins, there is a little bit ambiguity because of the ground truth and because the ground truth values and the generated value. But regression as does not have this problem. So what they are doing here is they are combining this, the classification loss here, which is this cross entropy. We have this log p of y given xi, and this should be log p of ti, which is again 1, and this is the classification error or cross entropy loss. And we have this regression loss, which is this mean square error loss. So zi here is the zi is the predicted regression value, and ti is the ground truth age value, and we are going to take the difference and square it, and we scale it by this parameter lambda. So this tells us like how much weight we should give for regression, and how much weight should, I mean, how much weight we should give it for classification. So use optimizing this loss using standard stochastic gradient descent with some learning rate will train the network and give us some uh, uh, good parameters which will do a good job on testing data. Let's see the results in the coming slides, but this is the overview of this X vector based age estimation model. And coming to the dataset, what is the dataset they used? They have used this 2008 and 2010's NIST speaker recognition evaluation dataset. It's called SRE8 and SRE10 data. It has around 11,000 utterances from a total of 1,227 speakers. There are some 769 female and 457 male speakers. And evaluation was done on the SRE10 telephone condition, where they have 5,000, around 5,000 utterances. And if you want to see the histogram of the age of the people with respect to the number of utterances they have, this is how it looks like. So they have this x-axis, which is the bins. You can think of like 20, age number 20, age number 30, or in between they have, I think this is a 5 year bin, and you can see the how many how much male distribution is, how much female distribution is. And you can see that the people with age 90 have very small amount of data, and the people in the range of like youngsters like 50 to 30 years old, they have a lot of data. And this is for the total number of utterances, and this is with SRE8 and this is with SRE10. And this is how the distribution of the data looks like with respect to the number of utterances, with respect to the age, or age versus the age in bins versus the number of utterances. So this is the data set used for evaluation or training. And we will see the baseline results. What they have done is they have created a baseline system, which is I vector system, and we'll see like how they trained on what data they have trained the GMM model, sorry, GMM UBM model to extract the I vectors. So the experiment, in the experiment, the architecture of the X vector network looks like this. So they have this 4 layer of TDNN, which is again, as I said, it's a time delay neural network. The first layer is a 400 size hidden size network with no context. I mean, that means every frame they are processing. And second layer takes context of 5, which is like -2, 0, 2. And third layer takes from -3 to 0 and 3. And fourth layer is does not take any context. And the output of the fourth layer, which is what goes into the statistics pooling layer, which will compute the mean and standard deviation of all the representations from each and all the representations computed at each and every timestamp, like 1 to 0 to capital T, or 0 to capital T minus 1. Then it pools it using this stats pool, which is computing mean and standard deviation of all the vectors, then concatenating them. That means they get around 1500 plus 1500 dimension, which is 3000 dimension of vector. That goes to dense embedding layer, which is again feed forward neural network, and they have this ReLU activation. Then there is one more layer of dense layer feed forward, then one more layer of dense softmax, which is what is used for classification, and then they use this affine for regression, right? So those are the layers of this X vector. And coming to the feature, what they have used is they have used 23-dimensional MFCC, and they compute this mean normalization over the sliding window of they compute it over 3-second window. Then they use this SAD, which is speech energy based speech non-speech segmentation for classifying non-speech or removing non-speech part from the audio content and using only the speech part, because non-speech part does not give you any information about the age of the person. Then for the iVector baseline, they have used this UBM, Universal Background Model, trained with SRA 4 and 6 English telephone corpus, which is huge data. And once they train GMM UBM model, they generate the iVectors after training this, after getting this total variability matrix, after training the iVector system. Then they can generate then they are generating the iVectors, and for those iVectors they have this they can fit DNN, or they can fit uh, uh, say, SVR, which is support vector regressor. So they think support vector regressor and DNN both gives almost same performance, and they have used this DNN for backend. So the input dimension for this DNN backend is 400 for iVectors and 800 for fusion experiment. We'll see what is 800 for fusion experiment. Fusion experiment is because it's nothing but combining both iVector and xvector for the final system. We'll see that. And for the performance measures, they have used this mean absolute error, which is nothing but just taking the difference between the ground truth and predicted value and summing over and computing the mean. And for they also use this Pearson correlation coefficient, which is computed like this. They have this mean predicted age and standard deviation predicted age for both ground truth and predicted value, and they use then they compute this Pearson correlation coefficient, which is tells you if the correlation is higher, then your system is better. So now we'll see some results. In the results, as we saw in the previous slides, we have this slide where we are showing this there is classification error and this regression error. So they have done an experiment where they set this classification error to 0 and regression error to 0 sometime, and they keep both of them with, and they see what is the accuracy. So if they set the classification weight to 1 and the regression weight to 0, you are sort of getting a very good accuracy in the sense we are getting around mean absolute error of around 5.1, which is good. But if they set the classification error to 0 or classification weight to 0 and regression to 1, then they are getting very pretty high mean absolute error. So this is actually error, lower is better, so this is bigger. So you can see this 5.1, there is a huge gap, right? But if I set the classification to 1 and regression weight to this very small value, you are getting a huge improvement, which is like uh, a little bit better than 5.1, which is good, right? Uh, then they have done some experiments on varying the training length segments and test length segments. As you can see, if the training length segments around 5 second, and testing length is around, I mean full testing length, you get a very good performance or very good mean absolute error here. And another thing you should observe is if the lengths are bigger, training lengths are bigger, and the test segments length, even if they are smaller, it works better, right? So this is the point they are trying to say. And at the end, at the last, they have this. They show how iVector and what is the difference between the iVector system and xvector system, and what will happen if they combine both iVector and xvector together. And they show some results here. So they have this iVector without LDA and with LDA. So basically, they had this 400 dimensional iVector vector, which they want to which they want to which they want to reduce the dimension to like very small number, which with using LDA. And they get this mean absolute error of 6.54 and Pearson correlation coefficient of 0.77, and overall you can see here the number. And but if you use X vector, they get 4.92, which is good, which is like better than iVector. And they also get some good results if they combine both iVector and xvector, concatenation basically. It's called fusion. So using these two together will give you very good Pearson correlation coefficient. As you can see, it's very good, right? And thanks for watching this video. If you have not subscribed to my channel, please subscribe for more contents like this, and see you in the next paper.